Hello students, welcome to the second lecture on the lecture series on relationship between numbers. Okay, so previously what we had learnt was we had learnt what are sequences, what are patterns, okay, what are different types of numbers that are important, that is composite numbers, prime numbers, what are the criteria to get to know that if a number is a prime number or not, or if a number is a composite number or not. And we also learned that one is a special number. Okay, all these things we have learned in the previous lecture. So let's continue it further and learn more concepts on it. Okay, so let's see, we have already learned that what are sequences. Okay, so let's see what are the types of sequences. One is arithmetic progression, one is geometric progression, and one is harmonic progression. Okay, so let's explore each kind of progression in a detailed manner. Okay, so let's start with arithmetic progression or AP. Okay, we may use this term more often than the whole word arithmetic progression. Okay, we'll be using AP more. So what the definition says us is a sequence is said to be in AP if the difference between any two consecutive terms is always the same. Okay, so if the sequence have A, B, C, D, E and so on, then B minus A is always equal to C minus B is always equal to D minus C is always equal to E minus D and so on. Okay, so if this criteria is fulfilled, then we say that the series or sequence is in AP or arithmetic progression, or the progression here is arithmetic. Okay, so the general form. Okay, let's see the general form of a arithmetic progression, where the general form is given by an is equal to a1 plus n minus 1 into d. Okay, so let's see what an is, what a1 is, what n minus 1 is, what d is, because without properly defining these terms, this is nothing but just a formula. Okay, it doesn't mean anything if we don't define each term explicitly. So let's do it. So a1 is actually first term. Okay, in the arithmetic progression, a1 is first term, a2 is second term, a3 is third term. Okay, so and so on, and d is the common difference. Okay, so d is nothing is but this is a4 and so on, and d is nothing but a2 minus a1 is equal to a3 minus a2, because they are same, the difference is same. So that is why this is called arithmetic progression and so on. Okay, and n is the term number. So a2 means second term in the sequence, and a3 means third term in the sequence and so on. Okay, so n is the term number, d is the common difference, that is this, and a1 is the first term. Okay, so let's learn a formula on this. So that is sum of first n terms. What is the sum of first n terms? If a1, a2, a3 is the sequence, arithmetic progression sequence. Okay, a4 and so on, then what is the sum of first n terms? Let's say at some point we'll get an, and then we'll also get the further numbers terms. Okay, so what is the sum of first n numbers? That is a1 plus a2 plus a3 plus so on plus an. Okay, so this is actually equal to Sn here. So the Sn is the sum of first n terms of an AP. So what it is equal to is n into 2 into a1 plus n minus 1 into d by 2. So d is the common difference, n is the number of terms. Okay, so term number and whole by 2 is equal to Sn. So if it asks us to, let's say for example, let's take the AP 1, 2, 3, 4, 5 and so on. Okay, so here a1 is equal to a2 is equal to 2, a3 is equal to 3, a4 is equal to 4, a5 is equal to 5 and so on. Okay, so this series is in AP. Why? Because a2 minus a1 is equal to 1, a3 minus a2 is equal to 1, a4 minus a3 is equal to 1, a5 minus a4 is equal to 1. Okay, and so on. Always the difference will be 1. So if we add this up to 15, let's say, okay, So what we will get is using this formula. So S15 is equal to 15, 2 into 1 plus. So 15 minus 1 is equal to 14, 14 into 1, okay, whole by 2. So this is the formula, okay. Let's see. So 15 into 2 into 1 is equal to 2 plus 14 whole by 2. So this is equal to 16 by 2 into 15, that is 15 into 8, that is 15 into 460. So 120 is the answer, okay. If we add, we also know the formula of adding the first n numbers in the natural number series, that is n into n plus 1 by 2. So up to 15, what the answer will be? 15 into 16 by 2, that is 8. So that is why 15 into 8 is equal to 120. So we can verify easily that this is actually the correct answer. So this is a manual verification that we did, okay. So the formula seems here to be correct, okay, or using the average of the first and last term. So we can also evaluate the same by doing this, n by 2 into a1 plus an. So in this case, what it will be is 15 by 2 into 1 by 2 plus, sorry, not 1 by 2, into 1 plus an is equal to 15. So this is equal to 15 into 16 by 2, that is equal to 120, okay. So the answer remains same, okay. Again we can verify this, okay. So let's go to the next slide. So common difference, the common difference d can be found using d is equal to a2 minus a1 is equal to a3 minus a2 and so on, an minus 1. So let's see the next kind of progression, that is geometric progression, and in short form it is called GP, okay. So the definitions tells us that a sequence is said to be a geometric progression if the ratio of any two successive terms is always a constant, okay. So the ratio, let's say a1, a2, a3 and so on, okay. If this is the a4 and so on, okay, if this is the geometric progression, okay, so a1 by a2 is actually equal to a2 by a3 is equal to a3 by a4 and so on. If this holds good, okay, holds true, then what we say is that the series or sequence here is in GP, okay, only by this condition, okay. So the constant ratio is usually denoted as R. So this is called as R. Okay. In the previous progression, that is arithmetic progression, we had found a common difference. Here it is a common ratio or constant ratio. Here it is denoted by R, the constant ratio, and there it was denoted by D, the common difference. Okay. So let's see the general form. In arithmetic progression, we learned the general form. Let's see the same kind of form here in the geometric progression. So if a is the first term, so the first term is a and r is the common ratio, okay, then the general form of a geometric progression is a r square, a r cube, a r power 4, a r power n minus 1, a power r and so on, okay. This will be the general form. So let's verify for the general term if the difference, or sorry, if the common ratio is actually constant, that is a by ar by ar square, okay, this is equal to 1 by r, this is equal to 1 by r. So what it seems is it follows the same, that is this is a geometric progression as it verifies the criteria, okay. So the nth term of a GP can be given as Tn is equal to AR power n minus 1. Okay, so this is the nth term. Since A is the first term, AR is the second term, AR square is the third term. So you can see the common pattern here, right? If we are telling about the nth term, this must have for nth term a r power n minus 1. So a r power n minus 1 is the nth term. Okay, nth term. You can see the pattern here. Let's denote these terms, that is tn, or what is a r power n minus 1. What are these? Okay, so tn is the nth term, a is the first term as we have previously discussed, and r is the common ratio, and n is the term that we need to evaluate. Okay, nth term. So n is the position of the term in the sequence. Okay, so let's find out the sum of gp. Okay, the sum of the first n terms of a gp when r is not equal to 1. What r is? R is here the common ratio, right? So if r is not equal to 1, then Sn is actually given by a into 1 minus r square whole by 1 minus r. Okay, if r is equal to 1, then the sum of the first n terms is simply n into a. A is the first term and n is the nth term position. Okay, so if r is equal to 1, this is true, and if r is not equal to 1, then this is true. Okay, you can't use the formula for r is equal to 1 here. Okay, if r is equal to 1 here, this will become undefined. Okay, so when if r is not equal to 1, this implies Sn is equal to this, is equal to Sn when r is equal to 1. Okay, so we'll see in an example in the upcoming lectures the use of these formulas. Okay, so let's see what an infinite geometric progression is. Okay, so what infinite GP is? So if mod r is less than 1, so if the common ratios modulus is less than 1. Okay, so basically the common ratio is in between -1 and 1 strictly. Okay, strictly in between. Then the GP has an infinite number of terms but a finite sum. Okay, so basically S infinity is equal to a by 1 minus r. Okay, you can see here why it is strictly less than 1. This formula holds good if r is not equal to 1. Okay, so S infinity is actually equal to a by 1 minus r. Okay, so let's see what harmonic progression is. So basically what the definition tells us is, if the reciprocals of a sequence of numbers from an AP, then the sequence is called an HP. So what you need to do is, if you are given a sequence A, B, C, D and so on, let's say, okay, then what you need to do is, you need to take their reciprocal. So 1 by A, 1 by B, 1 by C, 1 by D and so on. Okay, and then what you need to check is if these are in AP. If yes, then A, B, C, D are in HP. Okay, if no, then this is not in HP. Okay, so let's go further. So the general form is something like, let's say the sequence is A, B, C. Then for it to be an HP, the sequence 1 by A, 1 by B, 1 by C must be in AP. Okay, so this is the general form. So the nth term of an harmonic progression. Okay, so if A is the first term and D is the difference of the corresponding AP, then the nth term of the HP is given by, so basically Tn, let's say, is equal to 1 by An, okay, is equal to 1 by A plus n minus 1 into D. So An is actually equal to this. Okay, this An is actually equal to this. Let's see arithmetic mean. Okay, in harmonic progression. So if A and B are two terms in an HP harmonic progression, then their harmonic mean is given by HM is equal to 2AB by A plus B. So here to be noted is, if A and B are in HP, then harmonic mean will be the term between them. So if A and B are in HP and there is a term C, that is the actually harmonic mean, then it will be actually in the harmonic series itself, harmonic progression itself. Okay, so let's see the divisibility rules. Okay, so how can we know that if a number is actually divisible by 2 or not? Okay, so if a number is actually divisible by 2, if its last digit is even, so if you have a number, let's say xyz, okay, this is in the hundredth place, in the 10th place, or in the unit place. Okay, so in the last digit, okay, of that number, if that is divisible by 2 or that is even, okay, then what we can say is it is divisible by 2. So if I give you a number 1099765432176, okay, so this is a very large number. Okay, there are multiple digits here, okay, like 5 or 10 digit number this is. Okay, so what you can see here is the last digit is 6. By only seeing this one, okay, what we can say this is this number is actually divisible by 2. Okay, only the last digit matters. If it is divisible by 2, then the whole number is divisible by 2. Okay, so for example, another example what you can see is 246. Here the last digit is 6 and that is actually divisible by 2. So the whole number is actually divisible by 2. Okay, so let's see whether a number is actually divisible by 3 or not, and how we can actually see it. So in order to see it, what we need to do is we need to find the sum of its digits. Okay, so if it is x, y, z, so what you need to do is find x plus y plus z. Okay, this will be a finite number, and what you need to do is if this is divisible by 3. Okay, so let's say a number 13792. Okay, is it divisible by 3? So let's see. So 1 plus 3 plus 7 plus 9 plus 2. So 9 plus 2 is equal to 11, plus 7 is equal to 18, plus 3 is equal to 21, plus 1 is equal to 22. Okay, so 3 does not divide 22. So this is why this number is not divisible by 3. So let's see another example. So let's take 7, 8, 9. So what we need to do first is 7 plus 8 plus 9, that is 24, and 24 is actually divisible by 3. So this number is actually divisible by 3. And if you divide this number by 3, it will be something like 7, 8, 9, right? And divided by 3. So 2, 6, 1, 8, 6, 9, 3. So it is actually divisible by 3. Okay. This is equal to 0. Remainder is 0 and the divisor is actually 263. Okay, so let's see if a number is actually divisible by 4 or not. Okay, if a number is actually divisible by 4, then the last two digits, okay, when we see the divisibility of 2, okay, divisibility by 2, what we need to see is only see the last digit. But in terms of divisibility by 4, what we need to see is the last two digits. Okay, this is very crucial here. Here you need to see the last two digits. If they are divisible by 4, okay, the last two digits, okay, not separately but together. Okay, so if the number is x, y, z, w, then what you need to see is zw. So zw, so if I have 1, 6, 9, 4, 7, okay, what I need to see here is these two numbers together. That is, if 47, 4 divides 47 or not. Since this does not divide 47, so this number is not divisible by 4. Okay, but if I would have written 16948, this number is actually divisible by 4. Why? Because 48, 4 divides 48, that is why. Okay, so for example, another example is 1432. So is it divisible by 4? Let's see. As 32 here is actually divisible by 4, as it leaves with the quotient of 8. Okay, so the last two digits 32 from a number are divisible by 4, so the whole number is actually divisible by 4. So let's see the divisibility rule for 5. Okay, so when we can say that a number is actually divisible by 5, a number is actually divisible by 5 if its last digit is 0 or 5. The only thing that you need to see is the last digit, okay? And you need to see if it is 0 or 5. If none of these, then it is not divisible by 5. So if I have 1, 6, 7, 9, 0, 5, okay, this is divisible by 5 since the last digit is 5, okay, and 1, 6, 7, 9, 0, 3. The last digit is neither 0, nor 5. Since not this one, not this one, so this is not divisible by 5, okay. And another example is given here, 1450, since 0 is the last digit, okay, so it is divisible by 5. So let's see the criteria for the divisibility by 6. So a number is actually divisible by 6 if it is divisible by both 2 and 3, okay. So a number is divisible by 6 if it is divisible by both 2 and 3. So if you are given a number x, y, z, w, let's say, then what two conditions you need to see is, first condition is w must be even, because that is the criteria when it will be divided by 2, okay. And then what you need to do, calculate is x plus y plus z plus w, and see its sum is divisible by 3. Then only you can say that the whole number, this x, y, z, w, is actually divisible by 6, okay. So example is 198. So in terms of 198, what you can see here is the last digit is actually 8, that is even, okay. So this implies divisible by 2, and you need to see the sum. So 1 plus 9 plus 8, so 8 plus 8 is equal to 16 plus 1 17 plus 1 18, okay. So is 18 actually divisible by 3? So 3 divides 18, so this implies that 198 is divisible by 3. So this implies that 6 divides 198. You can conclude this from here, okay. So let's see the divisibility by 7. So when we can say that actually a number is divisible by 7, so what we need to take a look at is the last digit of the number, okay, double that digit, okay. Let's say you have x, y, z, w, so you saw w there, okay, and then you doubled it, so you got 2w, okay, and then subtract the doubled number from the remaining part of the original number. So this is what we had, okay. So what is the remaining part here? X, y, z minus 2w, okay. So if the result is actually divisible by 7, so if this is divisible by 7, or if we end up with 0, or only remaining, or this is equal to 0, actually this term, okay, star is actually equal to 0, okay, then the original number is also divisible by 7. Then we can see that this is actually divisible by 7. So let's see an example. So checking whether 532 is divisible by 7 or not. So take the last digit, that is 2 here, double it, that is 4, okay, then subtract it from the original, okay. So the remaining is 53 minus 4, that is what we have got, 49, and this is actually divisible by 7. So we can say that this is divisible by 7, and we can also see the example that actually the quotient is 76, okay. So let's see the divisibility by 8, okay. So a number is divisible by 8 if the last 3 digits form a number divisible by 8, okay. So you have x, y, z, w, y, y t, let's say, okay. So what we can see here is if the last 3 digits So the last three digits are these. Okay, if this is divisible by 8. Okay, then we say that the whole number is actually divisible by 8. Okay, so what we can say about the divisibility by 9. So a number is actually divisible by 9 if the sum of its digits is actually divisible by 9. Okay, again we take the track of 3, divisibility by 3. So you have x, y, z, w, t, okay, s, and then when we can say that this is divisible by 9 if x plus y plus z plus w plus t plus s is divisible by 9. Okay, so for example 2043, so 3 plus 4 plus 0 plus 2, that is equal to 4 plus 3 7 plus 2 is equal to 9. 9 is divisible by 9, so this implies that the whole number is actually divisible by 9. So let's see the divisibility rule by 10. So a number is actually divisible by 10 if its last digit is 0. Okay, so just remember that the last digit must be 0. For 540 we learnt that the last digit must be 5 or 0. Okay, in this case it is only 0, the only possible way. Okay, so 2370 is actually divisible by 10 because the last digit is 0. Okay, so it fulfills the criteria. And let's see the divisibility by 11. A number is actually divisible by 11 if the difference between the sum of its digits at odd positions and the sum of its digits at even positions is 0 or is divisible by 11. Okay, so for example what you can see here is 1925. Is it actually divisible by 11? So let's see. What we did was we took the even position digits. So 9 plus 5 minus 1 plus 2. So 9 plus 5 minus 1 plus 2. Odd position. Odd. Even. Even. Okay. So what we did was we clubbed them and added them, then subtracted one club from the other. Okay. So 14 minus 3 is 11. So if the difference, okay, of these even position addition and odd position addition is actually divisible by 11, then the whole number is actually divisible by 11. Okay, so let's keep it here. Thank you.